Hello.
Hello.
Yes, I can hear you. Can you hear me clearly?
Yes, madam, you are audible. Madam, namaste.
Yeah, namaste.
You are clearly audible, madam.
Okay, that's fine. If there is any issue with the sound or video, anything, please let me know. Okay.
Yes, madam. Yes, madam.
Hello and good afternoon, all of you. I welcome you all to this one-day international webinar on thermoplastic composites for sustainable future, opportunities with recycling, repair and reuse. Today our guest for the occasion is Professor Dr. Dipa Roy, who works as a lecturer at the School of Engineering, University of Edinburgh, UK. I welcome you, ma'am. I would also like to welcome our chairman and managing trustee, Sri Vinod Das, our principal, Professor Dr. Jogeshwari Rao, and all other dignitaries and participants to this occasion. Now I would request our principal, Professor Dr. Jogeshwari Rao, to please welcome our guests.
Good afternoon, one and all present here. Esteemed keynote speaker, Dr. Dipa Roy, respected chairman and managing trustee, Sri Vinod Das, distinguished guests, faculty and students from different institutions across the India. At the outset, on behalf of Synergy Institute of Technology, Bhubaneswar, I welcome you all to the International Seminar, Thermoplastic Composites for Sustainable Future, Opportunities with Recycling, Repair and Reuse. Friends, in recent years, the growth of continuous fiber-reinforced thermoplastic composites shows opportunities in transportation, aerospace, defense, industrial, renewable, and sporting goods. The global market of CFT is expected to grow at a compound annual growth rate of 9.5% from 2017 to 2022. The major driver is the growing demand for thermoplastic composites in different industries due to its higher performance and environmental benefits. This presentation will cover the manufacturing, properties and repair reuse potential of glass fiber reinforced acrylic resin matrix composites. In addition to this, a new generation of low-cost thermoplastic fiber metal hybrid laminates will be discussed by our esteemed speaker. Now, it is my privilege to introduce our today's speaker and my friend, Dr. Dipa Roy. Dr. Dipa Roy obtained her BTech and MTech in Polymer Science and Technology from University of Calcutta, India. She completed her PhD from Indian Association for the Cultivation of Science, Jadavpur University, India in 2002. Dr. Roy started her job as lecturer in the Department of Polymer Science and Technology, University of Calcutta in 2005 and continued till September 2011. In 2011, she joined Irish Center for Composite Research at University of Limerick, Ireland as research fellow up to 2016. She successfully completed 7 Government of India funded research projects as principal investigator. She has supervised 12 PhD students and 8 MTech students. Presently, Dr. Roy is a faculty at School of Engineering, University of Edinburgh, Scotland, UK. Now, I request Dr. Roy to present her webinar topic. Thank you.
Thank you everyone. First of all, I would like to convey my thanks to the organizers for giving me this opportunity today to present my work. And I'm really glad to be able to share our work with you. I'm now sharing my slides. Are the slides visible?
Yes, madam, it's visible.
Okay, thank you.
Yes, ma'am.
Okay, thank you. Thank you very much. Okay, so as I mentioned, I'm very thankful for really getting this opportunity to present my work and share the work with you all. And today the topic of my presentation is thermoplastic composites for a sustainable future, opportunities with recycling, repair, and reuse. Before moving on to the main technical presentation, I would like to briefly mention a few words about University of Edinburgh. So University of Edinburgh is one of the oldest universities in the world, and it was founded in 1582. Currently, its world ranking is 20. There are 5 campuses over the city of Edinburgh, arts and science and engineering, different faculties are in different campuses. School of Engineering is located in the King's Buildings campus. 4 different streams of engineering are there: mechanical, chemical, civil and environmental engineering, and electronics and electrical engineering. I come from mechanical engineering department. So mechanical engineering department is a very broad kind of, it has faculties from many different backgrounds, starting from physicists, engineers, chemists, and many really a variety of disciplines. And we have 7 research institutes there, and the research institutes are actually very interdisciplinary. So in each research institute, there are academics from all different engineering streams. So there is a very highly collaborative environment there. And not only within the School of Engineering, but there is strong collaboration with other departments as well. Like personally, I work a lot with the Department of Chemistry. And I think that helps the research a lot. These are some of the areas where our composites group is involved in. The composites group in the University of Edinburgh is not very old, actually. It started back in 2015 only, about 5 years old. But all the people who have joined this composites group are very experienced. So everyone has got above 20, 25 years of experience in the field of composites research. So I personally work on the 4 fields which are here. The first is the advanced thermoplastic composites, carbon fiber, polyether, ether ketone, and carbon fiber, polyether, ketone, ketone composites. We work with industries like Hexcel and Victrex, who are the leading oil and gas industries. The second area which I'm involved in currently is the liquid thermoplastic resin-based composites and hybrid composites. So this is actually my topic of presentation as well. And these composites are mainly targeted for renewable energy and marine sectors. The third area which I am involved in is the recycled plastics-based composites. So we are using recycled polyolefins and recycled polyethylene terephthalate. So they are all waste plastics, and we are developing some technology by which we can convert them into some value-added products. And the fourth area is a functional composite, mainly electrically conductive composites. I'm currently working. All are some sort of thermoplastic composites. Apart from that, there are many other areas where my colleagues are working, like thermosetting composites, which are mainly powder epoxy-based tape development. We have a pilot scale equipment in our lab. Composite design and manufacturing is a huge area, including digital manufacturing, which is a very emerging topic currently. Industries are all inclined towards digital manufacturing nowadays. And modeling is another very important area of composite research. Almost all experimental work is somehow linked with some modeling activities. And also a lot of focus is on additive manufacturing or 3D printing. So these are our general composite research activities in our group. I would like to mention in this context, this is a very interesting. We have strong links with different industries. So our research is a combination of fundamental as well as applied. So a lot of industrial PhD. So we work with some of these industries. I have put some of the names here. We're very much involved some way with these industries. And many PhD projects are actually funded by these industries. I have put this image here. I would like to mention briefly about this one. So you can see here, these are all waste actually bottles, PET bottles. So we have developed a technology where we are converting these waste bottles into some fibers by suitable formulation. And this fabric or fiber are actually working as thermoplastic prepregs for so this project is actually currently undergoing funded by UK government, and by next year we will get some results on the composite properties as well. Okay, so now I am actually coming to my today's presentation topic, which is in situ polymerized liquid acrylic resin based thermoplastic composites. So we all are familiar with composites, and as Dr. Raut already mentioned in her inaugural speech, that composites are now growing everywhere. And epoxy composites or thermosetting composites are more commonly used in structural applications. But they all are thermosetting composites are all non-recyclable in nature. So they are not really helping the environment. They are helping to substitute heavy metals. They are making the products lightweight. In that way, composites are really very welcoming, but at the same time, they are non-recyclable. So recently, there is a growing tendency to find out thermoplastic materials which can perform as good as thermosetting ones, and we can get structural composites with these thermoplastic materials. Now, this liquid acrylic resin has been introduced very recently in market, maybe in last 5-6 years. And this is a monomeric resin. Unlike conventional thermoplastics, it is a monomeric resin, which is available in the form of very low viscosity liquid. So before actually going in the presentation, I would like to acknowledge my group. So first, Ms. Winifred Obande, she is a PhD student with me. A lot of the work I'm presenting today is coming from her thesis. And also I would like to convey my thanks to Dr. Mamalis, who was a postdoctoral researcher, and my MIN students, and Professor Crowherd O'Brady, who is the head School of Engineering. So they are all involved in this work in some way or other. So I thank them wholeheartedly. Now, some background about these advanced composites. So composites are being used in aerospace, in transport sectors, in renewable energy sectors for last many years now. They are reducing the weight. As we mentioned, they are in fuel economy, or they make a flat sheet, and then we can by applying heat and pressure. So that's a big advantage for thermal. And another important advantage is the welding or the joining ability of thermoplastic composites. So that's another very big area of research as well, because whenever we join thermoplastic composites, there is always a weak point along the joining line or the bond line. But still, a lot of welded products are being used, and a lot of research is currently ongoing how to improve, we can improve the welds or the bond strength. So these are the main advantages which are making thermoplastic composites a really very good candidate for future products. But there are some challenges associated with thermoplastic composites. So we know thermoplastics are available either in the form of powder or pellet or granule, but they are all high molecular weight. Because of this high molecular weight, they have a very high viscosity. That's why it is not really easy to manufacture thermoplastic composites with fibers. So we have to use some high heat and pressure to weight the fibers or to impregnate the reinforcement materials with this matrix. And in a scale of viscosity, you can see how thermoplastics are, they are really placed high up. They are much, much higher in viscosity compared to the viscosity of conventional thermosetting resins, which are much more in liquid. High viscosity resin Thermoplastics are more conventionally used with practice for many decades now. We are mixing thermoplastic pellets with short fibers, and we are extruding into small pellets, and then we are manufacturing the product by compression molding or injection molding. So that's a more conventional practice. But if we want to manufacture structural composites where we have continuous fiber reinforcement for high mechanical load-bearing ability, their viscosity plays a big role. That's why there are some challenges associated with manufacturing high-performing continuous fiber reinforced thermoplastic composites. Now, there is recently in last few years, there has been a lot of development on thermoplastic tapes, where we have carbon fibers reinforced with different high-performing thermoplastic like polyether ketone or polyether ketone. But these kind of tapes are very, very expensive because of that high viscosity resin of thermoplastics. This is a liquid acrylic resin, a lot more expensive than epoxy. So the main advantage here is that in this liquid resin, so we can actually use the conventional manufacturing techniques which are used for thermosetting resins. Now, if we compare this performance of this amorphous material angle for polymers, so here we have the commodity polymers at the bottommost level, like polyethylene, polypropylene, polymethyl, methyl acrylate. Then comes the engineering polymers, and then finally the high-performing polymers like PEEK, PEC, all these polymers. So acrylics actually sit at the very bottom, and they are a commodity polymer, and they are purely amorphous. So when we talk about composites, most of the cases, if the composites are thermoset, we know they are cross-linked. So being cross-linked, they have their own inherent load-bearing ability. So they can perform well in combination with continuous fiber reinforcement. When we talk about thermoplastics, mostly we talk about semi-crystalline matrix for high-performing composites, like polyamide, polyether ketone, polyether ketone, all these are semi-crystalline thermoplastics. So we know in semi-crystalline thermoplastics, we have this crystalline domain, so we get much high mechanical property. So they are quite good, and they are compatible with cross-linked thermosets. But purely amorphous matrix like acrylic, we know that the matrix is rigid at room temperature when it is below its glass transition temperature. But if it's slightly enhanced, the temperature is slightly raised, then it will absolutely show a big drop in its mechanical property. As well as being purely amorphous, it will not have a good chemical resistance property. So these are all areas which we do not know how these composites are going to behave in future. And in addition to that, I would like to mention here that acrylics are also strain rate dependent materials. So they behave in a highly brittle way when there is a high strain rate loading is acting on it. In case of a low speed testing or a lower strain rate testing, they behave in a ductile way, but with the increase in the strain rate, they behave in a more brittle way. So that's another area which we do not know how these composites are going to behave in case of impact or other kind of a high strain rate testing. So we started our research by a benchmarking study where we actually compared an acrylic composite with epoxy, a standard epoxy composite. Glass fiber was the reinforcement. And here I would like to mention one point, that in any composite, we all know that interface is the most critical point. So interface has to be strong so that we can have that effective stress transfer at the interface of the fiber and the matrix. Now, so when we select the reinforcement fiber, here glass fiber, it is important that it has the right sizing agent which can actually interact with the matrix. So we selected a glass fiber reinforcement fabric which has a multi-compatible means it is compatible with epoxy resin as well as it is compatible with acrylic resin. So it has got those silent coupling agents which has got those R groups or the organic groups which are chemically compatible with different matrices. Now, since our acrylic resin is a liquid monomeric resin, it polymerizes in situ during the composite manufacturing. So there is a high opportunity of actually forming some covalent bonds between the resin and the sizing agent during the composite manufacturing in situ. So that's a big advantage of actually acrylic resin, because we are getting a chance of forming some covalent linkage between the sizing agent and the matrix, which can actually help in effective stress transfer at the interface. But this is the manufacturing we used in our lab. So this is a vacuum-assisted resin transfer molding. We used a tool, a glass top tool. So here the mold is about 500 millimeter by 500 millimeter. So it's a quite big panel. And since it's a tool-based vertem, that's why we can really have a very good quality consolidated laminate. And the repeatability is very good, and the void content or the defects are minimum compared to conventional tabletop vertem. So we used this acrylic resin from Arkema, and we used epoxy resin, which is a standard epoxy. And we manufactured 2 laminates, very similar, keeping everything similar, the glass fibers the same. So the layup, number of layers, the layup sequence, everything was kept the same, matrix or the resin. Now, we saw that in case of epoxy composite, the total filling time for the mold was about 27 minutes, which is quite standard with any standard epoxy resin. Whereas with this acrylic, main reason is that very low viscosity of acrylic. So it flows really fast, and the overall impregnation is very quick, and the production or the manufacturing can happen in much shorter time. So since everything was done in a very similar way, so we did a comparison, and there was a clear advantage of using this kind of thermoplastic resins. Now we measured the glass transition temperature of both the composites. So we tried to select epoxy matrix, which is quite close, because we know epoxy resins can have TG from 60 degree, 50 degree, 60 degree to up to 180 degrees. So we tried to select a grade of epoxy which is quite close to the acrylic resin. So the glass transition was about 119 degree for the epoxy, and for the acrylic it was 106 degrees. So they are pretty close. But what is the common what we expected is a high damping property for this acrylic composite. So here we can see the damping parameter tan delta is much higher. This is what we expect from a thermoplastic composite anyway, so it was no surprise. But the storage modulus values were pretty close. So overall, the indication of the mechanical property or the elastic component of the composites were quite close, which is a good positive sign. I will not go in detail of the mechanical characterization, but this is just a overall view of what we observed by a thorough mechanical characterization. So when we compared the mechanical properties, tensile strength, both longitudinal, transverse, interlaminar properties, damping capacity, everything between acrylic composite and the epoxy composite, they are pretty much at par, quite close. The only difference was the transverse tensile property for this acrylic composite was about 33% higher, which was quite significant. Capacity was higher as well, as we discussed in our previous slide. But this transverse tensile, since it's a transverse tensile property, so it's dictated by the matrix. It's dominated by the matrix behavior. So clearly this result showed that acrylic matrix was performing quite well in case of, in the transverse direction. So this was really a very good observation, and we are very happy to see this result anyway. Now, we also investigated the interlaminar fracture toughness of both the composites, so acrylic and epoxy. And we followed this ASTM testing, ASTM D5528. So this is a double cantilever, how the samples look like. And by doing this test, the initiation toughness of the acrylic was marginally higher than epoxy, and the propagation toughness was quite higher, significantly higher than this epoxy. It means that, as we expect, the toughness, fracture toughness of the acrylic composites are quite good, as we expect in case of thermoplastic composites. And this was observed because this testing is a quite slow strain rate of testing. The strain rate is quite low. We use about, I think, about 2 millimeter per minute kind of speed, which is quite low. And with that kind of low speed of testing, acrylic behaves in quite a ductile way. So that played a big role. And we saw a big advantage of this higher fracture toughness. Now, so apart from this mechanical characterization, we also wanted to find out how this liquid resin actually helps in the repair or in joining activities. Because it's a monomeric resin, there can be a very good opportunity actually to bond in situ during the repair or the joining or welding. So that's an advantage which we do not get in case of conventional thermoplastics. So we actually did a very simple experiment. This was a master's project actually. You see, we manufacture similar equivalent laminates, but one laminate we manufactured in one step, which was we took 8 layers of glass fiber and we infused the liquid resin. Then the resin polymerized in situ and we got the consolidated laminate. And we manufactured the same laminate in 2 steps. In 2 steps mean, first we took 4 layers. We infused 4 layers with liquid resin. Then it was polymerized, and then we used that polymerized laminate with 4 dry glass fabrics, and then again reinfused the resin. So in the second step, actually, the whole laminate was consolidated together and we got the laminate. So the final layer in this laminate and the first class, it was done in 1 step. This was done in 2 steps by 2-step resin infusion. Now we are calling this second one as the bonded laminate. We characterize these laminates to understand if this joining layer, having this joining layer in the meat plane, how actually this is going to affect the mechanical properties. Now the observations were very, very interesting. So we saw that in case of transverse tensile properties, the transverse tensile strength, it was higher in case of the bonded laminate. The interlaminar shear strength were pretty similar in both, which is quite obvious because they are the same matrix. But this is a very interesting observation because whenever we are manufacturing in 2 steps, we are infusing the steps, we are really getting some benefit. This is contrary to what we see in case of conventional joined laminate. If we actually join a conventional thermosetting laminate or a thermoplastic laminate, we always have a weak point in the joining plane. So normally the stress concentration is much higher there and the failure occurs from that weak bonding line. But in here, we saw just the reverse because it was somehow the overall property was really enhanced. And why this happened? Now, this is a very interesting observation. We were very delighted when we actually saw these results. So what's happening in the first case when we are actually manufacturing the laminate? In the first go, the resin is being polymerized and we are getting a polymerized laminate. So this is the first step of the infusion. Now when we are actually reinfuse it in the second step, again the liquid monomer is being infused with the first laminate. Now this liquid resin is actually acting as a reactive dye, the first laminate. Because of this resin, what's happening at this interface or at the joining plane, this matrix is being dissolved partly with this infused liquid resin. So this is an advantage of having the amorphous matrix because amorphous matrix is absolutely highly susceptible towards attack by solvent. So here, this liquid resin is acting as a reactive solvent. It is dissolving the polymer at the interface, near the interface, and then it's in situ polymerizing. So we are getting here a semi-interpenetrating polymer network actually at the interface. So this is enhancing these properties. So instead of having a weak bond line, we are having a very strong bond line where we have these IPN, semi-IPN kind of a formation. And this was theoretical, we thought this is going to happen, but with the experimental results, we saw exactly the same results. So this opens up a very good opportunity actually for repair and joining of this kind of laminates. Now this is, we have actually communicated this work. This has not yet been published. So, I think we have not seen yet any repair or joining work with this kind of resin before. So we hope this would be an interesting result to share with the scientific community when it gets published. Okay, now, in spite of having so many different opportunities and advantages with the acrylic resin, there are some concerns how this acrylic matrix is going to perform in high-performing composites. So this is not actually time-tested, and a lot of queries are there from the industries, like if we use acrylic matrix composite, how they will perform in the long run, we do not know. So there are a lot of opportunities to modify the matrix to bring some more reliability on the performance of the matrix as such in long-term applications. So this is, we discussed this before. So we have this amorphous matrix, whereas we don't have any cross-link or any crystalline domain. So they are very susceptible to heat distortion or chemical attack. So there is an opportunity to enhance the performance of this amorphous material so that they can perform well in more demanding environments, in high loading conditions, high strain rates, or in case of higher service temperature. So this was something we actually took as a extension of our first set of work. And we had to select some modifier polymer, because the main purpose of the modification is enhancement of the property, but at the same time, you have to keep in mind that the recyclability should not be actually lost. We have to retain the recyclability, which is critical for future sustainable materials. And at the same time, we should not increase the viscosity of the resin significantly so that the manufacturing is hampered. Because here, the room temperature liquid resin infusion is critical. It's very important. If we increase the viscosity by some modification, then that is not going to help the infusion process. So there is a limitation how much we can modify. So these two are the most critical considerations when we thought about this modification. And so we have to retain these two, and then at the same time, we have to have some improvement in the chemical, mechanical, or thermomechanical behavior of the product. Now we selected a material, polyphenylene ether. We worked with SABIC actually. So this PP is from SABIC. We have some working relation with SABIC. So we got materials from them. And we selected polyphenylene ether with the functionality. So the functionality at the chain ends actually was very helpful in producing some reactive blending during the composite manufacturing. Now, why we selected polyphenylene ether? Polyphenylene ether, we already know that it's a very well-performing engineering thermoplastic. But the main problem with polyphenylene ether is that they are very poor processing characteristics. So they are very hard to process. In spite of having very high good mechanical property, they are poorly processable. That's why most of the time, polyphenylene ether is used as a modifier with other resins. So this is a well-established modifier for many thermosetting resins. But using this polymer as a modifier for acrylic resin has not been tried before. So this was another interesting study. So we did not really know whether what kind of sorry, do you have any noise? Sorry. Okay, so polyphenylene ether is a thermoplastic, engineering thermoplastic, unlike acrylic, and they have a low tendency to creep, and they have high resistance to solvent. So these are the main reasons why we selected engineering thermoplastic. And you can see here the comparison of acrylic and polyphenylene ether. So compared to acrylic, the strain at break of polyphenylene ether is much, much higher. So although it's an amorphous engineering thermoplastic, but it has much higher breaking strain, which might be helpful for acrylics. And apart from that, the glass transition temperature of polyphenylene ether is 160 degrees, so which would be helpful for enhancing some overall thermomechanical behavior of the acrylic matrix composite. So this was the main motivation why we selected polyphenylene ether. And it has got the functionality what we wanted to have for reactive blending with the acrylics. Now, we actually prepared 4 blends, varying the ratio of this polyphenylene ether between 3 to 15 wet%. And you can see here, these are some of the scanning electron micrography of the blends. So first one is the neat acrylic. This is the pure acrylic resin. These are some of the voids. This resin is very prone to foaming when we want to cast at room temperature. So it's very hard to prepare pure acrylic samples. Now, when we have the blends, then the foaming tendency is reduced significantly. So we don't see any void in case of the blends, but we can see these zones. I'm not sure if you can see properly. There are some small zones here, which are actually, but they're very well bonded with the acrylics. Now, with the increase in the percentages from 3 to 15%, this the second phase, you can see how it looks quite different. But what we can see from these micrographs is that there is a very well bonded polyphenylene ether dispersed phase present in the overall matrix. So now we selected actually, okay, so this is another micrograph. This was generated by confocal Raman microscopy. So here the blue phase is the acrylic phase and yellow phase is the polyphenylene ether. So we can see here how more or less uniformly this polyphenylene ether is dispersed in the acrylic matrix. And we also tried to understand the chemical composition by Raman spectroscopy, but we haven't yet completed those tests or analysis. That's why I haven't included that in my presentation. But overall, this can give a very clear picture how this polyphenylene ether is actually dispersed in the acrylic matrix. Now we did some solvent resistance test. Acrylic resin is absolutely highly susceptible towards solvent attack. So if we put a neat acrylic sample in a solvent, you see within kind of 2 hour, 3 hour, all the sample is fully dissolved. So here we have the pure acrylic sample and we have the blend samples. And within few hours, the acrylic actually vanished. It completely dissolved, but all the blends, they were still there till the end of 72 hours. So that was a very positive indication that we are enhancing or improving the solvent resistance of these matrix, which might be really beneficial when they are being used in some demanding environment. These composites are being used in some demanding environment. We selected one blend actually with 5% polyphenylene ether, and we tried to do some mechanical testing, very preliminary mechanical testing with the unreinforced matrix. These are not composites, these are unreinforced modified acrylic matrix. So with some simple testing, flexural testing, we saw that there is a significant enhancement in the modulus of this blended material. So here, even with 5% of polyphenylene ether, the modulus increased significantly from 30. So this is the stress, sorry, this is the strength. The strength increased significantly from 30 to about 54 MPa. So this was a good indication that we are going to see some enhancement in the mechanical properties as well. But this is a pure unreinforced matrix. So we do not know how this enhancement is going to be transferred in the composite, because in composites we know we have those fibers present. So the behavior of the matrix are very much controlled by the presence of the fiber or influenced by the presence of the fiber. But anyway, this was a very good indication that we can have some enhanced mechanical performance in terms of the matrix as well. Now we saw some micrograph of the fracture surface. So this is how we fractured the sample, and we saw these micrographs, and we could see some zones of these polyphenylene ether zones, but the ductility was still there. So we can see here the flaky nature of the matrix, which is quite visible in case of pure acrylic. So that was still there in case of these blends, but at the same time we saw some significant enhancement in the strength or the mechanical behavior of the blends. Now we did some solvent resistance test of the composite. The previous one was the unreinforced matrix. Now we use some composite. So this was a composite. P0 means there is no modifiers. We have this glass fiber and pure acrylic matrix, and the other one is the glass fiber, acrylic, and with 5% of our modifier polymer, PPE. Now, when we actually immersed the samples in acetone, 5 to 120. So this is actually happening because of those dispersed phases. So there is a pure acrylic phase as well as a mix of PP acrylic as well as PP on its own. So there are different phases present in the matrix which are giving this broad glass transition behavior. Now, these are some of the fracture surface behavior of the modified acrylic composite. I don't know if you can really see some difference or not, but there are some differences. So here, in case of pure acrylic, the top layer here, the top row actually, it's quite flaky and the matrix is more or less homogeneous. In case of modified acrylic matrix composite with the PPE, we could see a lot of fibrillation. So under fracture, when we actually did some flexure testing, there were a lot of fibrillation in the matrix. So the behavior of the matrix was quite different when this PPE was actually incorporated in the system. So some difference was expected, and so a lot of energy was absorbed in this fibrillation as well. So the overall the energy required during the fracture was quite different in case of the modified composite. Now, we actually did a lot of different characterizations, and this work was done in collaboration with chemistry department, Dr. Jennifer Gordon, and her PhD student, Veronica. So they carried out a lot of testing on NMR and GPC. And after significant experimental characterizations, we finally came to some conclusion that what's happening whenever we are incorporating this reactive PPE, we are keeping the thermoplastic matrix overall, but we are creating some cross-linked, giving that rigidity to the material, which are actually enhancing the solvent resistance property, but still the overall material is remaining thermoplastic. So we are able to deform or repair or reshape the materials. We are not losing its recyclability, but that incorporate some rigidity in the overall matrix through these small cross-linked regions. We did a lot of different characterizations. I haven't incorporated everything, but the thermal degradation behavior was enhanced. We saw some change in the exotherm in DSC. That was because of the reaction happening between the functional polyphenylene ether and the acrylic. There was quite many different mechanical property as well. So this was a very new observation for us because we could retain the thermoplasticity, but we could enhance some of the drawbacks of the acrylic matrix. Now we are planning some future work where we can optimize the dose of the polymer, and we are also in touch with SABIC. They are very interested to extend the work, and if we have further opportunity to do more work in this area, then we try to optimize the dose. We can try to optimize different catalysts or the initiator type, and it would be interesting to see how the fatigue behavior of the modified composite is changing, how the creep properties, which are more time-dependent properties, are changing, how the strain rate dependency of these acrylic composites are changing on modification. And another important property which would be area of interest in future is the flame resistance, because especially for marine industries, flame resistance is a big criteria. So we don't have any information till now how these materials or the modified materials are going to behave in case of fire. So these are some of the open areas which we will be looking into in future. And like one new PhD project will be starting very soon, and that's mainly with one industry, that would be with marine structures. So flame resistance would be a very interesting area of research for that. And renewable energy sectors have a lot of interest for thermoplastic resins, and with this kind of liquid resin, actually it is possible to manufacture large structures. So there is a significant interest from the renewable energies industries, like if they can use these liquid thermoplastic resins for big blade structures. And for blade structure, fatigue is a key property. So it would be very interesting to find out the fatigue behavior of these kind of composites or modified composites. Now, from this, I will move on to the thermoplastic fiber metal laminates. This is also based on this liquid acrylic matrix. Now, being this liquid in nature and being monomeric in nature, this gives us a lot of material or to bond the material with other materials. So that's the main reason why we thought of manufacturing hybrid composite with this particular liquid resin. Now, there is a background for this kind of hybrid fiber metal laminates. So these fiber metal laminates are already exist. They exist since 1980s, and they are mostly aerospace grade materials which are manufactured from epoxy resin and from aluminum alloy and glass fiber, mostly glass fiber or carbon fiber or aramid fiber. But what is the main advantage of having this kind of hybrid laminate? The main advantage is that they actually combine the superior properties of the composite, which are good fatigue properties, lightweight property, and the very high ductility of the metals. So we can combine the good properties of both the constituents, and we can produce a new material which can actually give us a combination of good fatigue resistance, lightweight, as well as high energy absorbing behavior, a high impact strength. So these materials are already being used. Glare is one material panel for aircrafts. Three different types of hybrid, these fiber metal laminates, all are thermoset epoxy based, and they are called glare. Glare is for glass fiber, aral is for aramid fiber, and caral is for carbon fiber. So you can have different fiber reinforcement, mostly with aluminum alloy, different aluminum alloys, and epoxy resin. Now, these fiber metal laminates are manufactured in autoclave and they are pre-preg based. So they are very, very expensive materials, and they started since the 1980s, but still they are limited in aerospace. So there is absolutely diversification of the application of these fiber metal laminates because of their cost and their manufacturing. Also, there is another important point to mention. When these laminates, hybrid laminates are manufactured, cured normally about 1/6, and aluminum has a very different thermal expansion coefficient than the composites. So during this manufacturing, there is also at the interface of the composite and the metal. So those residual thermal stress can act as a point of failure in application during the service life. That's why there are a lot of other post-processing steps are carried out in case of these laminates to make them less prone to kind of failure from that interface. But because of all these reasons, these thermosetting hybrid laminates are limited to aerospace. Now with this liquid resin, actually we got an opportunity to diversify this and to manufacture thermoplastic fiber metal laminates by liquid resin infusion at room temperature, which is the main advantage because we are doing all the manufacturing at room temperature. So if we can manufacture such hybrid laminates at room temperature, then we can avoid having those residual thermal stress at the interface because the curing is not involving any high temperature. So in spite of having a mismatch in the thermal expansion coefficient of the composite layer and the metal layer, still we can manufacture effectively without adding those manufacturing stress factors. This work was actually funded by EPSSC Future Composites Manufacturing Research Hub feasibility study, and we manufactured successfully these thermoplastic fiber metal laminates. Now, in case of such hybrid materials, the most important consideration is the interface, because we are trying to bond the composite with the metal. And in case of liquid acrylic resin, we are actually manufacturing and bonding in situ during the composite fabrication. So it is very important that the surface of the metal is prepared enough so that it can have the right bonding with the composite, because they are very dissimilar materials, chemically very different. So they don't have any affinity to bond with each other. That's why we have to have a right surface treatment of the metal alloy to make that ready for bonding with the manufacturing. Now, we tried different chemical and physical treatments. So first one is, you see here, this one is actually the degreased aluminum alloy surface. We didn't do anything on this surface. The surface looked like this after degreasing and cleaning. And then we tried alkaline treatment, we tried acid treatment, we tried anodization, which is more industrial technique, and also some atmospheric plasma. So with all different techniques, we then investigated the surface morphology with the scanning interferometer, and we also how this surface of the aluminum alloys look like, and this is already published in 2019. And so with those surface treated alloys, then we manufactured by room temperature vacuum resin infusion by the same technique what we used in case of glass fiber composite alone. And this was all done at room temperature. And aluminum alloy sheets had very fine holes so that the resin can permeate through the aluminum alloy sheets, and we can have the right weighting throughout the bulk of the composite. Now, this was our actually methodology. So what we did, we took the metal alloy, we had a bonding layer or an adhesive layer, but the adhesive did not have any curing agent. We didn't have any hardener in the adhesive. So what we did, when we infused the resin actually, the initiator present in the resin cured the adhesive. So there was a bonding between the liquid organic layer and the resin matrix. So there was an in situ bonding between the this metal and the composite during manufacturing. So this was a very interesting way of bonding the metal with the composite, and we were very successful in doing this. And we measured some mechanical properties. So this was some of the properties, preliminary studies. This is already published in this paper. So here the metal was alkali treated, and we compared the flexural modulus and the flexural strength with the standard glass fiber acrylic composite. And we saw that the modulus was quite high and the strength was slightly lower. And in case of interlaminar shear strength, there was a quite reduction in the interlaminar shear strength of this hybrid laminate, the fiber metal laminate. This was lower than the next step was how we can actually enhance this interfacial bonding, because the performance of the hybrid composite will be completely dependent on the interface. If the interface is not strong, then these fiber metal laminates will not be able to bear the load properly. So this is critical to have the optimum interface. So in case of a purely glass fiber acrylic composite, this is a homogeneous system. So it has only the glass fiber and the acrylic resin. So in that way, it's a homogeneous system. So this can have a very good interfacial bonding, whereas in case of fiber metal laminate, it's a very heterogeneous system. So it has got composite and it has got metal. So there are dissimilar materials. So the joining of the dissimilar material is always a weak point. That's why we wanted to make this bonding as strong as possible, so that we can have these hybrid materials performing well under different loading conditions. Okay, so these were some of these images of the interface of the composite and the metal from our first set of laminates. So here you can see this shows a quite good bonding. The lower layer is the metal layer. This is the composite layer. This is the interface. So it looks really facial gaps, anything present. So this very liquid viscosity, or the low viscosity of the acrylic resin, is actually highly beneficial in weighting the metal surface. It can flow very well, and since the surface preparation also facilitated, so that's why we got a quite good interface even in the very first set of our studies. And this is in the composite layer. So the fiber matrix bonding in the composite layer was very good as well. So overall, this was a very interesting or a very positive start of this research. Then we tried to optimize the interfacial bonding so that we can have the best mechanical property out of these fiber metal laminates. So here you see this is the reference laminate where we have only glass fiber and acrylic composite. It's a more homogeneous composite system. Whereas with different bonding agents, we tried 6 different bonding agents with different combinations. So we could achieve much higher interfacial strength than what we saw in our very first study. So we could actually, the interlaminar shear strength was pretty close to what we see in case of a purely acrylic glass composite. So there was a significant improvement in the interfacial bonding by changing or optimizing the bonding agent type. So this is the flexural strength. So here again, we could see that with these different bonding agents, the flexural strength exceeded what we saw in case of the pure composite. So this was a very positive result, what we saw by changing the type of the bonding agents. Now with this optimizing this bonding, by optimizing this bonding kind of type, bonding agent type, we then started to find out what would be our drop weight impact property, because for this kind of hybrid laminate, the key point is how good these laminates are in resisting high impact. So the aluminum alloys, being highly ductile, can play a big role in absorbing these impacts, high sudden impacts. So whereas composites, they don't have those good impact properties, especially acrylic, being a strain dependent matrix, they do not show any advantage in drop weight impact property. So it is important that if we can find out a way of enhancing the impact strength of the laminate, then that can work well in many sectors, including defense. So this was the main objective for this work. We tried manufactured different laminates with different positions of the aluminum alloys, and this was again done by master student, and this was done in collaboration with the Cranfield Acknowledge, Dr. Hamid and Dr. Pavan and Dr. James Watson, who were very helpful in the collaboration activity. Now these three different types of laminates were manufactured. So first one was all glass acrylic composite. The second one had this aluminum alloy layer in the mid plane, and the third one mid plane. The main objective was to compare the energy absorbing ability of these laminates. So we wanted to compare a pure glass fiber composite with the composite having one aluminum layer, having 3 aluminum layer, as well as to have a comparison between when we have 1 layer and 3 layers of aluminum. So these are some of the experimental plan we made, and we used a drop weight impact tower in Cranfield University. So they have a very big impact center, many drop weight impact towers. So we used one of the, this is how these the indenter looked like, the impactor tip actually, how it looks like. And this is the standard process of drop weight impact. So it was following an ASTM standard. So we know on drop weight impact, we can have the absorbed energy as well as the elastic energy. So more is the absorbed energy. It means the material is able to absorb energy that might be via matrix cracking, via debonding, via some deformation. And this elastic energy is more with what is coming from the rebound of the impactor tip. So this is the standard curve what we get by drop weight impact test. Now we measured these the laminates we manufactured, and there was significant difference in the drop weight impact behavior of the laminates when we had this aluminum layer sitting there. So here you can see the force, and the force level was very different. And this is force versus time, force displacement, and energy time. So here, in case of the pure glass laminate, which is the blue one here, we can see the absorbed energy level is about 10 joule. Whereas when we have one aluminum layer sitting inside, the absorbed energy level increases to about 20, so it doubles. It means that if a hybrid laminate like this undergoes a sudden impact, then it would be able to absorb a lot more energy. And that energy actually, here this energy is being absorbed by this interbonding overall composite. And the aluminum alloy itself, aluminum alloy is a highly ductile material, so it can undergo a lot of deformation and absorb the energy. So this kind of interfacial debonding and the absorption of energy by the aluminum alloy can actually prevent perforation of the overall composite structure. So in that way, this can be highly advantageous. We can have a lot more impact resistance out of these kind of combinations. Now, when we had 3 layers of aluminum, you can see we have 3 layers here. When we are comparing with in comparison to a pure glass acrylic composite, we can see the energy absorption behavior is changing significantly again. So here, having 3 aluminum alloy layers, it is absorbing much higher energy. So it has the aluminum alloy even on the surface. So when there is an impact, the surface can absorb a lot of energy. And this, when dissipated throughout the bulk, it has got, again, aluminum alloy. And so the overall, the impact which reaches the lower level is much less. The overall absorption is much, much higher. And so this clearly shows the benefit of actually having these metal layers bonded with the laminates, with these glass fiber composite laminates. So this is again a comparison when we have this aluminum alloy at the mid plane, and when we have the aluminum alloy at the three different layers. Here again, as we see, having the aluminum alloy is definitely helping, and having more number of aluminum alloy is helping a lot. Now there is a lot of design opportunity with this kind of fiber metal laminates, because we can vary the thickness of the composite layer. We can vary the fiber orientation in the composite layer. It can have 0-90 orientation. It can have plus minus 45 degree, depending on what kind of mechanical property we want to have in the final product. It can have very different fiber orientations, thickness, and the number of layers in the composite. We can have different arrangement of the fiber of the composite layer and the metal layer. We can have very many different metal alloys in as the metallic constituent. Here we are using aluminum alloy 6086 grade, but it is very common to use the 2000 series of aluminum alloy as well, and also some magnesium alloys. Magnesium alloys are very extensively used in aerospace because they have some inherent benefits. So there is an opportunity actually to combine different types of metal alloys of different thickness, different types of composite layers of different thickness, different types of fibers. It may be glass. We have done it with glass, but it is possible to use other fabrics like aramid or carbon. In case of carbon, there might be a problem of galvanization, because of carbon fibers are conductive by putting a thin glass layer between the metal and the carbon composite layer. So there are a lot of opportunities here to actually combine different materials and different orientations, and we can get very different properties. Acrylic liquid matrix, it is varying from marine structures to defense, and we are currently also undergoing a project, UK government project, where actually we are manufacturing this, these composites for renewable energy sectors. And finally, these hybrid thermoplastic composites can be highly impact resistant, and they can be designed in different ways. They are repairable, reshapeable, and we can have a lot of benefits to manufacture products which are sustainable. Thank you. So I come to an end. Thank you very much for your patience and for listening to the presentation.
Madam, actually, there are some questions.
Yes, please.
Actually, Madam, Dr. Jarif Joseph has asked a question. What about the pyrolysis?
Sorry, can you repeat, please? I couldn't hear, please.
Madam, actually, Dr. Jarif Joseph
yes.
has asked a question. What about the pyrolysis?
What about the pyrolysis? Pyrolysis.
Oh, pyrolysis of what? Sorry?
Pyrolysis of composite, I think.
Okay, so pyrolysis of composite is for recycling. A lot of pyrolysis is presently being done for thermosetting composites. But for thermoplastic composites, we can actually shred and we can reuse in different products. Pyrolysis is not generally used for thermoplastics, but more for thermosets.
Okay. Madam, there is another question from Partha Pratima Das.
Yeah.
Can we enforce natural fibers such as jute, hemp, glass with liquid acrylic resin?
Sorry, the sound is breaking. Can you, repeat once more, please? I can't hear you properly.
Can we enforce natural fibers such as jute, hemp, glass with liquid acrylic resin?
Yes. Yes, we can use these natural fibers. The only thing, we have to have the right sizing agent, because natural fibers are highly hydrophilic, whereas this resin is more hydrophobic. So unless we have the right sizing agent, the bonding will not be good. There are some published papers already where they have used these natural fibers, flax or hemp with the liquid acrylic resin. But it's important to keep in mind about the sizing agent. We need to have a right sizing agent on the natural fibers to have a good interface with this matrix.
Thank you, ma'am. Now the question.
Dipa, sir. Dipa, I have one question.
Yes, please.
What is the major bottleneck of using acrylic resin in composites?
What is the, sorry, what is the?
What is the major bottleneck or
Okay.
disadvantages of using the acrylic resin in composites?
Okay, so first one would be, I would first start from manufacturing. So from manufacturing, acrylic resins are they have a very strong smell. So it's important during manufacturing, we have to keep a closed system. That's important. That's a very basic point, but it's important to keep in mind during manufacturing. And in performance, actually, being amorphous, as I mentioned, the main problem is some of the temperature dependent and the chemical resistance related. So those are some drawbacks in the properties. And apart from that, I don't see any real bottleneck actually in using acrylic resin in high performing composites.
Another question, what is the potential of natural fiber in hybrid metal composites?
I think it is definitely worth trying because the only thing is we have to ensure that it applies the same, if we have a right bonding between the natural fibers and acrylic matrix, then it is possible to have a strong composite layer. Then we can ensure the bonding also with the metal. The bonding with the metal can have the same way what we are doing now, but the bonding with the natural fiber has to be just done properly. Otherwise, it would be interesting combination to see actually,
That is also very challenging. That we were also doing.
Yeah. That would be challenging. More the materials and dissimilar materials, more challenges in combining them effectively, So they have to perform at par under the same conditions. They are being so different structurally, chemically. So we have to bring so that they can behave in the same way under the same conditions. So yes, quite a bit of challenge involved.
And what is the advantages of using the acrylic polymer with the polyester in performance and in cost? What is the comparison?
Okay. So unsaturated polyester resin is very much cheaper. I would imagine it would be cheaper, but they are all much cheaper, but they are all thermosets. So they are not recyclable. And if styrene is a reactive diluent generally used with unsaturated polyesters or vinyl esters, which is not environmentally friendly right now. So there are a lot of regulations coming where you can use the health hazards, health and safety hazards where these styrene liquid diluents are there, so which is not ideal. But in acrylics, we are getting the product which is thermoplastic and recyclable. I think that's the big advantage.
Okay. Ramesh sir, any other questions from audience?
Madam, there is a last question that Sujit Kumar is asked. What are the major drawbacks of using acrylic resins in terms of environmental challenge?
Okay, so acrylic resins are not a green resin or bioresin, so they are not environmentally friendly. But the products are thermoplastic. So once they are polymerized, and they are recyclable, repairable, reusable, in that way they are sustainable. But if we consider the resin as such in liquids from a petroleum-based material, so it's not environmentally friendly that way. It's a chemical, complete chemical. But once polymerized, they give a product which is sustainable that way. So we can say in that way it has got some advantage environmentally.
Another question from my side. Dipa, can you hear me?
Yes, I can hear you clearly.
You have worked both in India and outside. What you are feeling? What is the difference?
Okay, so I think it depends on very much on how you work, like on the person, how we work, you know.
Environment, opportunity.
Yeah, I think yes, infrastructure is a big advantage, I would say. We have a really good infrastructure. If you have a real good infrastructure, that helps in a lot of research, in getting the funding as well, because in order to get funding, you have to deliver. You need the right infrastructure as well. And I think what the thing which I enjoy most doing research abroad is the collaboration. There is a lot of collaboration opportunity. I think that's something which is really good, because one person cannot be expert in everything. You know, you have people who can contribute really well in different fields. Like as I mentioned, we are collaborating with the chemistry department, and they are excellent. You know, like absolutely brilliant in the way they are supporting our work. I think that's something which is I would definitely like to see in my own like previous places, you know, or in any place, anywhere in the world. I think collaboration is a key, encouraged and practiced more.
Okay, Ramesh sir, any other question from audience?
Madam, actually, there is another question from Dr. Jerry Joseph, that she wants to know catalysts which are good for plastic pyrolysis. Can you please explain that?
Sorry, your sound is a bit broken. I can hear Jogeshwari properly, but no, sorry for that.
The question is, catalysts which are good for plastic pyrolysis. Can you please explain that? I think the question is not clear.
Pyrolysis is more in nitrogen environment is done, and I don't think I'm not sure, to be honest, but I have never done pyrolysis myself, so I don't think I can answer that. But as far as my knowledge is concerned, do we need catalyst for pyrolysis? I'm not sure, to be honest. I don't know.
And as you are working in, I think I think that you are not dealing with the pyrolysis part.
No, even I work with the thermosets. Even I'm working a bit with thermosets as well for over 20 years, but still I never really had to do any pyrolysis. So pyrolysis is more done when you are involved in direct recycling of thermosetting composites, you know. So I don't have any in-depth understanding or knowledge on pyrolysis.
And also many of the audiences, they are asking for your email. So if we give permission, then we'll...
Yeah. It's there in the website. If you search my name, you will get it in the university link is there. So you can get all information from there.
So thank you, Dipa. Very interesting and informative presentation. And I hope that the researchers and faculties, definitely they will be benefited. And thank you very much for accepting our invitation. Now I request our Mrinal Madhusunda madam to propose the vote of thanks.
Thank you, ma'am. Thank you so much for this very informative session. I really put forward my heartfelt thanks to our guest, who is also our chief speaker, Professor Dr. Dipa Roy, who, in spite of her busy schedule, she has given her time and effort to us. I would also like to thank our chairman and our managing trustee members for giving their cooperation and coordination to for the relentless support for coordinating this webinar. I would also like to thank our technical and non-technical staffs as well for their support and cooperation. And lastly, to all our participants and our dignitaries who have really made this webinar a success. Thank you, ma'am.